This is denser than this is. Will you accept that?
Yeah.
Okay. So, by your reasoning, this one should win. Oh, that's hollow, sorry. I didn't want a hollow one. There we go. Aluminum and steel or iron. Pretty darn close. Density is not the whole thing. Although you act, when I said before, mass is not the whole thing, there is a little bit more. Density adds a little bit of a touch to it, but density is not the whole story either. Ms. Goff, then Elaine?
So, we're still giving speculations, correct?
Yeah.
Okay.
Yeah.
So, I was thinking, like, the reason I really kept choosing tie is because I was thinking of, like, like a book and a feather. But I know that's probably different now because it's not just free falling, I guess. It's not just in the air. Now there's a surface involved, so is friction a factor? Or is that not?
All right, so the factor of the friction should be plain here is I want the table to be low enough that it will roll properly as opposed to just skimming over the surface, but steep enough so that it actually will roll. And so it needs to be going fast enough so that the bumps in the table don't affect it, but low enough so that it actually rolls. The friction is what is causing it to roll. So if it slid some, if these things slide as they're going down there, then we are dealing with another factor, which I hope by having it at just the slight angle, we avoid. So friction does play a role in the fact that it causes them to roll. Hopefully it's not doing anything other than that. I do not know why. Sometimes I can just push a button on the side and it will stop ringing, and other times it doesn't. Sorry about that. Okay. Elaine.
Well, to go off of what she said, I think, actually, what they both said is, actually, all three of them, is the shape has to do with, that's why the ball beat the cylinder, is the shape. But the reason the ping pong ball was beat by the rubber ball is because the rubber ball had more grip, more friction, so that roll was more productive. But then the density, and so I kind of think it's kind of an all of them play a factor in it, you know?
So if I erase these two, this one would win?
Well, no, because see, that one, the density is in, this one's beneficial, the shape, this one's beneficial. And then, I don't know.
Let's find out what happens. If you want to do a side bet with the person next to you, go for it. So the steel won on that one.
And the weight has to help it get that grip to get going, whereas the ping pong ball doesn't really have a good grip, so it just, you know.
Yeah, and again, I'm hoping that it's not so steep that it's going to be, that's a significant factor.
So, you probably already told us, but I can kind of confused. Well, if you drop those two, or
Right.
is that like a totally different topic?
That's a, say totally, it's still physics. If I'm dropping the two of them, they should fall at the same rate. But there's no rotation involved, so that really is sort of a separate. It's the idea that rotation brings into it that we're sort of addressing right now.
Oh, sorry.
I need to apologize.
Would it be the circumference? Because if it's smaller circumference, wouldn't it roll faster?
We did the tube Yeah. We raised these two and it was roughly a tie.
Would it be that, that one, the rotation is faster than that one, because that one is,
I will agree, the rotation was, well, let's see. The linear speed was definitely faster, the radius was smaller, so Omega would be bigger than that one. But the question is why? Before we address that. These two objects have the exact same mass, the exact same length. The difference between the two is that, and I'm hoping you can see it, that there's holes over here and here that you should be able to see through. If I can rotate it so there'll be some orientation that you can see through it. And then it's dark in the middle, where my hand is. This one is the reverse, where the holes are in the middle, but it's dark on the outside. I'm hoping that you can see that well enough. So the mass is the same, the only difference is this, the black spots there is the mass that they have inside, and so on this one the mass is here, and this one the mass is here. So, if I want to whip them back and forth, which one's going to be easier to do?
Red.
The red.
The red one.
And that's not just because my left arm is weaker than my right arm. That one's easier, I can even switch. Almost hurts.
So while you went through all of that, all I was thinking about was, I thought it would take more energy to get the heavier one moving, and that's why they would move at the same rate. But
It- Heavier is not the whole thing that goes along with the mass. There's more to it than that, because these have the same weight,
it takes,
but this takes more energy to zip back and forth than this does.
so like when the weight is distributed like more towards the center of it, that makes it go faster?
Yes, in essence.
Okay.
So, it's not just the mass or the density, it's how the mass is distributed in the object. That is the key.
I could not say that right, that's what I was thinking, like, go ahead.
I mean, that's the part of the process is,
Yeah.
Like skiing,
pardon?
like skiing, where you go slower, you spread your body out, and when they wanna go faster, that's their body.
Oh, and skating also. The skater with arms out like this will go more slowly than when they bring them in. As you distribute the mass outwards, what's happening here is
You're going slower.
this becomes bigger. Because the moment of inertia is dependent upon the mass and where it is, how far it is from the center. So as that mass moves out, even if I have the exact same weight between the two objects, the exact same mass between the two objects, as R gets bigger for the mass, I gets bigger. As I gets bigger, more of the kinetic energy gets wrapped up in getting it to rotate, and there's less left over in order to actually move down the ramp. So it's not ultimately, and now you might be going, wait a second, if I have a more massive object, doesn't have more kinetic energy, doesn't require more kinetic energy to rotate. Well, yes, but it also has more energy to start with. The mass actually cancels out, and that's beyond the scope of 110 to show that. But occasionally I do have an individual who wants to see how the mass cancels out, and I'll be glad to show you at some break or afterwards if you would like. So distribution of mass is key. The more it is, as Brittany was saying, the more it's distributed to the outside, the harder it is to rotate, the more inertia it has. And that's demonstrated there. So, that is moment of inertia. And we probably should take a break and, yeah, I'm not seeing a lab happening today, because I think you've got plenty to do as it is. So, let's Take 5. And, oh yeah.
All right.